learn how to use them. And well, probably most of us know this, and I believe that most of us will actually make a personal hello with one of those lanthanides named gadolinium. When you basically require to get MRI, you will get injection of gadolinium sulfate as a contrast, okay? So those elements play enormous role, and Victoria will talk about them, what we do here with them.
Good morning, everyone. My name is Victoria Beck, and I will be talking about the electrolytic deposition of lanthanide alloys from deep eutectic solutions. So there are 14 lanthanide metals, and they are also called intertransition metals and rare earth metals. They are used a lot in technology, especially in computer hard drives, because they form very strong magnets. And I have some magnets I'm going to pass around. So now you're probably wondering, what are deep eutectic solutions? So deep eutectic solutions are a class of non-aqueous ionic liquids that are formed by Bronsted, Lowry, or Lewis acids and bases. There are several types of deep eutectic solutions, but top 3, which is formed by choline chloride and a hydrogen bond donor, is the most versatile. So these solutions are actually very, very viscous at room temperature, but once they're heated to about 100 degrees Celsius, their viscosity is similar to that of water. And one of their most important features is that they can dissolve in ionized transition metal halides and oxides, meaning that many metals can be electrolytically deposited from these solutions. So first we prepared our lanthanide chlorides from lanthanide oxides, and we did this by dissolving 0.01 moles of lanthanide oxides in 20 milliliters of 39% hydrochloric acid and 10 milliliters of water. So these were cooled, and then the precipitates were vacuum filtered, washed with acetone, and then dried under vacuum at room temperature. So then we prepared our deep eutectic solutions, and we did this by mixing 1 mole of choline chloride to either 1 mole of malonic acid, 2 moles of urea, or 2 moles of ethylene glycol. And then we heated those at temperatures not exceeding 100 degrees Celsius just until a uniform liquid was formed. So then we did electrolysis, and we did this using either graphite or nickel electrodes at constant voltage and at a temperature of about 80 degrees Celsius. We analyzed our metal deposits using a PC microscope and scanning electron microscope, and the elemental composition of the deposits was determined using scanning electron microscope, but particularly EDS, which is energy dispersive X-ray spectroscopy. So now I'm going to take a minute to talk about all these pictures up here. Hopefully all of you can see most of them. These are just structures. This is choline chloride, malonic acid, urea, and ethylene glycol. These are our solutions here. This is choline chloride with urea, malonic acid, and ethylene glycol. Hopefully you can all tell that this is clear from, especially those in the back, that these are clear. So this is nickel electrolytically dissolved in choline chloride and urea, and choline chloride and malonic acid. This is neodymium chloride and choline chloride and ethylene glycol, and this is cobalt 2 chloride and choline chloride and ethylene glycol. For the 4 down here, the solvent was, again, choline chloride and ethylene glycol. This is copper 2 chloride, this is cobalt 2 chloride hexahydrate, this is neodymium chloride and samarium chloride, and this one is copper, cobalt, neodymium, and samarium. So I'm going to come over here and talk about these two. Well, first let me mention these electrodes. Okay, so this is our graphite electrode. These are our nickel electrodes. You can see that there's a very thin layer of copper on each electrode. So these are cyclic voltammograms. Basically what these tell us is what potential samarium or cobalt is reduced, which is important for us because we need to know what voltage to set our electrolysis at, because this is actually not really well documented in these solutions. And these are both dissolved in choline chloride and ethylene glycol, and this was run with platinum electrodes at room temperature. So this is a deposit of 10 on a graphite electrode. Hopefully, we probably can't really tell, but these are 10 peaks, which means that we have confirmed that there's 10 deposited on this electrode. But we also have this little bit of chlorine right here, which I'll mention in a few minutes. So this is copper on graphite electrode. Again, we have a lot of copper deposited, and again, this little bit of chlorine. This is copper, cobalt, neodymium, and samarium on graphite electrode. There is a lot of copper, and there's a pretty good amount of lanthanides deposited there too. This is copper, erbium, neodymium, and samarium on graphite electrode. This is before sonication and this is after sonication. All sonication did was remove the layer that was not actually deposited onto the electrode. So we have a lot of copper on this one and some lanthanides, and then again this fluorine right here. This one is cobalt, copper, neodymium, and samarium on the nickel electrode. The primary peak here is nickel, which makes sense because the electrode is made out of nickel. And this here is copper, but notice there's not very much lanthanides on here. So for our results, we discovered that electrolysis resulted in very thin layers of lanthanides deposited on our electrodes. And while lanthanides were deposited on nickel and graphite electrodes, more lanthanides were deposited on the graphite electrodes than the nickel electrodes. These graphite electrodes contain chlorine, which originated from choline chloride adsorbed on the graphite electrode. And tin can be deposited, but only using choline chloride and malonic acid because it forms insoluble complexes with urea and glycol. Any questions?